Hello folks, let's talk about high availability in PostgreSQL. Whether we like it or not, our PostgreSQL deployments can be impacted by an outage. You can run your PostgreSQL instance in a cloud region and then an availability zone can go down, or an entire region can become unavailable, or your operating system can fail you. You want to be ready for a myriad of reasons that can bring down your database. So that's why let's review different PostgreSQL high availability options, and we are not going to search for any silver bullet solution. There are many ways to approach high availability in PostgreSQL, and all of those ways depend on your deployment option. We will review 4 different deployment options. The first one is single database instance. You have just a Postgres instance running in your private data center or a cloud region, and this instance handles all the reads, writes, and all other types of requests, and you certainly want to make it highly available. Another deployment option, number 2, is the same single primary instance can be complemented by read replica nodes, and those read replica instances can help you to boost read requests by taking a chunk of the requests from your application. When your PostgreSQL database needs to scale horizontally, then you need to deploy some multi-master solution, and we also need to see how to make our multi-master solutions highly available. We will talk about 2 deployments. The first one is with a coordinator, and the second one is without a coordinator. Alright, when we are talking about high availability, we do not confuse it with disaster recovery. Because high availability is the ability of your system to operate continuously by eliminating a single point of failure. For instance, if you have a single database instance that processes all the requests, this is your single point of failure, and you need to improve your high availability. While the disaster recovery is the process of getting a system back to an operational state. For instance, you have your single primary instance of Postgres, it goes down, and then you need to follow some steps to get it back to normal. So generally speaking, high availability and disaster recovery are very well connected, but they are different things. And today we are going to talk about high availability. So let's talk about the first deployment option. When you have a single primary instance of Postgres and you want to make it highly available, how do you approach it? First, you need to add standby instances. Also, you need to use some solution to replicate changes from the primary to the standby. And when we are talking about the failover and failback solutions, so generally speaking, you don't want to do everything manually. You might have some manual procedures, but in the ideal world, you want to automate everything as much as possible. So when we are talking about different built-in replication solutions, in PostgreSQL, we have streaming replication. All the changes that are written to your write-ahead log file of the primary instance can be replicated to your standby database node. And here is you need to keep in mind that with the streaming replication, the entire database is replicated and the configuration of the primary and standby has to be the same. There is another type of replication that is built in PostgreSQL. It's called logical replication. Again, your primary instance writes all the changes to the write-ahead log file, and then those changes are decoded and sent to your standby instance. So here is an advantage is that you can replicate specific tables if you don't want to replicate the entire database, and the configuration of primary and standby can be different. So at least 2 options, but definitely PostgreSQL and the ecosystem of PostgreSQL solutions have many more replication solutions to offer. Next, when you are using a built-in replication solution such as the streaming replication, you need to decide on your synchronous commit mode. For instance, the remote apply mode, the strictest one, will require your primary instance to wait for the commit to be fully written to their standby instance in such a way that if anybody decides to read this change from your standby, the change will be visible immediately. And this is an example of a fully synchronous replication between the primary and standby. At the same time, you can relax this mode. You can set the mode such as the remote write. In this case, the changes will be synchronously committed on the primary instance, but then the primary will send this change asynchronously to your standby, and the primary will not be waiting while standby commits this change locally. This is an example of an asynchronous replication. When it comes to failover and failback, there are several different solutions. One of their widely used options is pgpool and Patroni. For instance, pgpool supports not only failover and failback, but also connection pooling and load balancing. Patroni makes things a little bit more automated and flexible, and it depends on etcd or alternate solutions for consensus protocol. Okay, so we are going to review both solutions, but we will start with pgpool. All right, now let's put all the pieces together, how a sample configuration can look like for this deployment option. So let's say we are deploying everything in a cloud region A, and we have some client application that connects to our PostgreSQL instance through some virtual IP address, and this virtual IP address can redirect traffic between their availability zones within this region. So first, our primary instance is live and healthy, and the client requests are sent to the pgpool instance, the active instance in zone A, and then that pgpool instance forwards the requests to the primary instance, and the changes are replicated from the primary to the standby using, let's say, streaming replication. If you are using some type of synchronous replication, ideally you need to have at least 2 standbys. Because if you have a single standby, and if that standby goes down, that your primary will stuck. It will not be able to proceed with the changes until the standby is back to normal. And when it comes to pgpool, you have a standby pgpool and zone B as well. And there is a special watchdog process of pgpool that monitors the healthiness and the state of the pgpool instances. Okay, now let's say that you want to scale read. So what if your deployment option is single primary Postgres instance, but also you have read replicas? In this case, you still have your primary instance, you have some failover, failback solution, and you have some replication mechanism, but also you can use standbys at the read replica nodes. Those read replica nodes can float your primary instance by processing read workloads. And if you use those read replica nodes, you also need to have some load balancing solution, because a load balancer can redirect your read requests across primary and replica nodes. When we are talking about few popular load balancing solutions, again, there are many. You can continue using pgpool because in addition to the failover capabilities, it supports connection pooling and load balancing. Or another typical configuration is to use HA proxy for load balancing of your TCP and HTTP traffic, and then you can use pgbouncer for PostgreSQL connection pooling. So let's take a look at the sample configuration with a single primary database instance and their single replica node. Again, the only difference here is that instead of a standby, we have a replica in zone B. We have the same replication solution. And here is the client application. Right now, our primary instance is live and healthy. So the client requests are routed to pgpool in zone A, and then the pgpool can load balance reads between the primary and read replica. If there is a write, all the writes go to the primary node. Okay, so it's all simple. Moving forward, what if you need to scale horizontally? In the beginning, you might need to have a server with 32 CPUs, but then over the time you need to scale because you're getting more traffic, you're getting more data, and you are upgrading to a machine with more resources. And then if you need more, you keep scaling vertically. However, at some point in time, you can hit the ceiling. You might not be able to find a machine with enough resources to suit your workload, or it can be prohibitively expensive. It can happen. So this is the reason when people use horizontal scalability, and when we are talking about deployment, how can you scale out Postgres? Because by definition, Postgres scales vertically. It's a database that runs on a single server, but you can use sharding. The concept of sharding is that you can split your entire database into shards. So instead of having one massive and big PostgreSQL instance, you can have multiple smaller instances, and each instance stores a subset of your data. So when it comes to PostgreSQL sharding solutions, you can implement it manually, or you can take advantage of already existing solutions. For instance, one of the solutions is CitusData. It's an extension for PostgreSQL for sharding. You have your client application, and you have already sharded your Postgres instance into multiple worker nodes. So those worker nodes are PostgreSQL instances. And your client application needs to connect a special coordinator node, because the coordinator knows where each shard is located and where a particular record should be stored or queried from. PostgreSQL instances, they do not communicate to each other directly. They cannot do this. They're not designed for that. That's why you need to have a coordinator. And let's say that the application wants to select all the records from the cards table. It sends this request to the Citus coordinator, and then coordinator forwards this request to all of the PostgreSQL worker nodes. When you are inserting or updating data, the client sends this insert to your Citus coordinator, and Citus coordinator takes the primary key and calculates a shard. And then in this example, the coordinator knows that this new record should be stored on the node number 1. And now let's talk about high availability, because this is the simplest deployment option when you have multiple worker nodes and you have Citus coordinator and you have a client. But we want to make this deployment option highly available. How do we do this with CitusData? First, all those worker nodes are primary PostgreSQL instances that just store a subset of your data. And as with the previous deployment options, you need to complement them with standby instances. So every PostgreSQL worker needs to have its own standby instance. And you can use streaming replication, logical replication, or whatever works best for you. And if it's synchronous replication, again, keep in mind, you need to have 2 or more standby instances, because if any standby goes down, your primary worker will not be able to move forward. It will stuck until that standby is returned back to normal operations. So this is the first step. After that, you need to introduce a failover and failback solution. CitusData natively integrates with Patroni, which helps you to automate failover and failback, and you need to run your Patroni agent alongside your primary Postgres instances, standby Postgres instances, as well as near the coordinator. That's not it. Patroni requires you to use a third-party solution for consensus, because all of those Patroni agents send statuses of their instances, and they need to decide collectively when you need to switch from one primary to standby, or when you need to do a failover from the primary coordinator to the standby coordinator. And they use etcd cluster for this consensus protocol. And you can use some other solutions. And that's not it. You need to have some load balancing solution. You can use HA proxy, and the client application connects to this HA proxy. And if everything looks healthy, then the HA proxy will be forwarding your traffic to the primary coordinator, and the coordinator will be sending the requests across the primary PostgreSQL instances. And alongside those primary Postgres instances, you need to have a pooling solution. You can use PG Bouncer. So every instance also needs to have its own PG Bouncer, because all those primary instances and standby instances are standalone PostgreSQL processes. Finally, let's talk about the final deployment option, multi-master without coordinator. This deployment option is for those who would like to have a sharded version of PostgreSQL so that you can scale horizontally, but you want to simplify your architecture. You don't want to have an architecture with so many components for failover, for load balancing, for PG Bouncer, standbys, etc., etc. You want to have something simpler. But if you want to eliminate the coordinator from your architecture, you need to find a solution where PostgreSQL instances can talk to each other. That's why you can consider YugabyteDB. YugabyteDB is an open source distributed SQL database. It's built on PostgreSQL, and it comes with a distributed storage layer. It has 2 components. It has distributed query layer, and this is basically PostgreSQL source code with enhancements. And its distributed storage layer supports distributed transactions. It shards all your data, it load balance all of your requests, and it makes sure that everything is consistent, because it implements the Raft consensus. How YugabyteDB handles data distribution and how it synchronizes changes. So in this configuration, we have a 3-node YugabyteDB cluster, and all the data is sharded. So every shard is either a leader or follower of a Raft group. For instance, you have a shard number 1, and this is one Raft group. The leader of the group is node 1, which means that this shard and this node will be getting all of your application requests for the data that belongs to this shard. If you do any update, this update goes to this shard number 1, and this update is synchronized to the follower shards on node number 2 and node number 3. And at the same time, shard number 2 leader can be on node number 3, meaning that node number 3 will be handling all the reads and writes by default for all of the data that is in shard number 2. And node number 2 is the leader for the shard number 3. And this is how you can load balance nicely your write and read requests with this distributed architecture. So now let's see how YugabyteDB simplifies your configuration. So this is the application architecture with a centralized SQL database. You have your application instances. Those application instances use PostgreSQL drivers. The drivers connect to load balancers, and then you have connection pooler, and then depending on your deployment option, if you're using read replicas, your reads can be load balanced between primary and replica, and there is a synchronization between primary and replica. With YugabyteDB, you can eliminate a lot of the components. You just have your multi-node YugabyteDB cluster that can scale vertically as well as horizontally. Your applications can connect to those nodes directly, and you can use your PostgreSQL standard driver, or you can use enhanced YugabyteDB smart driver. Your application can open a connection with node number 1, then the driver will learn the IP addresses of the other nodes, and it will be load balancing automatically the requests across the entire cluster. And this deployment option is highly available, because if any of YugabyteDB nodes goes down, then the other cluster nodes will detect this quickly within several seconds, and they will be handling the traffic that were previously going to the failed node. So it's all easy, and you don't need to have any third-party components, coordinators, etc. Alright, so now you know that there are multiple high availability options that exist for PostgreSQL deployment. Select an option that works best for your deployment, whether you use a single primary instance, or you use single primary instance with read replicas, or you have a fully distributed and sharded YugabyteDB cluster. There are various ways how you can improve high availability in PostgreSQL.